composite system. Again, it's not clear at the moment, but it will become clear via examples in the next couple of sessions. Right? I'm just throwing these two new labels at you, coupled in the sense of connected somehow, and uncoupled, like independent, not connected. But what is connected or not connected, and what does connected mean, and stuff like that. All that will become clearer. Okay? Right. So yeah, it'll become clear with examples. Well, I'll give you a bit of a taste. Coupled. If the orbital angular momentum and spin angular momentum are disconnected in some way, then they are uncoupled, not connected. They're not. There's no, due to the presence of the orbital angular momentum, there's no force on the spin, or vice versa. That kind of thing. They're sort of independent, disconnected. To start with, right? Now we'll start our first concrete example of a composite system. So we're going to add two angular momenta, and one of them will be of type orbital angular momentum, and the other one will be of type spin angular momentum. Right? So speaking generally, remember we had J1 hat, J2 hat, and J was sort of a generic operator. It could stand for either an orbital angular momentum or a spin angular momentum. So here now we've got a concrete case. So we're taking a simple case. We just have one electron. Okay, so it's, when we say it's composite, we don't mean like two electrons. In this case, I mean it could be, but we're just talking one electron in this particular example. Keep it simple. But the two angular momenta are the orbital angular momenta, the L, of this electron, plus the spin angular momentum, S, of the same electron. Okay, so this J here refers to the total angular momentum of one electron. Okay. Now we can split up this J in terms of components. You can't see it in the previous session, if you remember. We had three components, Cartesian, XYZ axes components for J hat. So we had the XYZ components of J hat would be JX hat, JY hat, JZ hat, right? And we can do the same thing for the L hat and the S hat. So that the X component of J hat would then be just LX hat, SX hat, and similarly for the other two. So JY hat would be LY hat plus LS hat, and so on. Okay? Now, we've done earlier, we know the commutation relations. If you apply the commutator, sorry, to for like two L's, for example, Lx comma square brackets Lx comma Ly, that commutator, we know the answer. And similarly for S, or say Ly comma Lz, or Lz comma Lx, we know those commutation relations for L, and similarly for S. So I've asked you to do for homework to show that J squared and Jz commute. I was mentioning that a bit in the previous session, right? Now, you might have a bit of a query. Well, what do you do with the mixed when you have like an L operator and an S operator together, like a kind of product? What happens then? Well, they commute because the L and the S, they operate on different things, so they don't influence each other. So, an L operator and S operator you can assume commute. Okay? And then via that, do for homework, show that the j squared hat and jz hat, when you split up the j's into these components, and you know the commutation relations for the l's and the s's, so therefore you can deduce the commutation relation between j squared and jz. In fact, it's 0. You know, the commutator is 0. In other words, these two, they commute, and therefore they have the same set of eigenfunctions. So what our target here, these two equations, is starting to be fulfilled, right? Because we've now shown that these two, for homework, that they commute, and therefore they have a common set of eigenfunctions, right? Now the analysis, it was quite a several pages of textbook. The analysis for when we had L hat to get the eigenvalue, we'll go through that again, in this case with J, and see if you can get, instead of L times L plus 1, you get J plus 1. See if you can do that. And similarly, the eigenvalue for the projection, or the component of J along the z-axis, so Jz, that its eigenvalue is Mj, right? And we're assuming that J is larger than the modulus of Mj. Does that make sense? The analogy with little l here, it would be greater or equal to the absolute value of m. Now, what's the lowest value of m? Well, it's minus l. Remember, m ranges from minus l to plus l. So, by analogy, J would satisfy this inequality as well, because if this is L, it would be greater or equal to the mod of ML. So the lowest value of M would be minus L, mod it, so it's just L. So L is greater or equal to L, in this case equal. But you could have an M value of 0. Okay, that would be the smallest modulus. So that would make L here greater than 0. So it's greater or equal to. So that seems plausible for J, because it works for L and for S. And S is the same. Alright? Now I've sort of cut myself in mid-sentence, so let me just finish off the sentence and show that these J's here, these little J's, they're the eigenvalues of the total angular momentum, that they are half integral. Right? So, using all this stuff. So, there's quite a bit of homework there. So, also show that these J's here are half integral, right? And the spin quantum number is, for which, where the spin quantum number here is half. S is a half, right? That's given. You're told, well, you know already, because the eigen value for the spin angular momentum is a half. All right. Okay. Now next session or two, be warned, the intellectual level goes up a bit, quite a bit. It gets tougher. We're into Lecture 9 in a senior level course, merging on towards first year master's level, so bit of a general comment. If you're a university student, ask yourself, at your university, what proportion of bachelor level students go on to become master's students? I've taught at 3 different universities, one in America and 2 in China before I retired. And if I remember correctly, in the US, maybe somewhere between a 1/5 and a 1/10. So somewhere between 10 to 20% of bachelor students, probably more like 10% I think, went on to do masters. So the level that you'd expect masters level students to be able to cope with reasonably readily would be quite, a lot more difficult than the material that the average bachelor student could cope with. Now, given we're up to lecture 9 now, so now this is an introductory text to quantum mechanics, sort of an overview, and towards the end of the course, getting close to master's level, so you expect the standard to rise somewhat. So I'm sort of warning you what's coming in the next couple of sessions, right? It's going to get harder. And while I'm at it, I might as well say a similar comment about the proportion of master's students who go on to become PhD students. That's a lot tougher. I remember, what are PhD students? They're effectively future professors. I mean, why do people become PhD students? A lot of them, either they want to become professional researchers in, say, research labs, like national labs and that kind of thing, or become professors. And professors are expected to do research and publish research papers and so on. And so PhD students, what they're learning in effect is how to extend the frontier of knowledge. Whereas a master's student, so by the time you're finishing, say, second year, in terms of coursework, the courses, say second year master's student, you're pretty well expecting to be reaching the frontier of knowledge, in the specialties you've chosen to learn. Now, that was true a couple of decades back. Personally, for these deGarisMPC courses, I have 2 more teaching levels, course levels above N2, second year masters. So there's PhD 1, PhD 2. So it just gets harder and harder. That's just the nature of the expansion of knowledge, human knowledge. There's just exponential growth of knowledge. The human knowledge doubling time now is, it must be months, must be less than a year now. It's frightening. It's just, it's exponential. All right. So expect next couple of sessions to be quite a bit tougher.